one of the goals of group theory is to be able to distinguish between groups that look alike, that are in some sense an incarnation of the same group, and groups that are fundamentally different. There are several different ways one can do that, and one helpful notion that allows us to, in certain situations, say that two groups are actually fundamentally different is the notion of an order. One type of order we're going to be talking about, it's the order of the group. The other, more refined version of it is the order of the elements in a group. So we start with the order of a group. What is it? That's actually a very simple notion. The order of a group G is just how many elements it has. So it's the number of elements in G. Sometimes a group can have finitely many elements or infinitely many elements. So you can have a group of finite order and of infinite order. In either case, this is the notation for the order of G. So for how many elements it has. So let's just quickly do a few examples. However, this notion is really simple, so I'm not going to spend too much time on it. What's the order of the group of fifth roots of unity? Well, how many fifth roots of unity do we have? Zeta 5 squared, zeta 5 cubed, zeta 5 to the fourth, and 1. There are 5 of them. So the order of the group mu 5 is 5. How many elements do we have in the group Z mod 2Z? How many congruence classes do we have mod 2? There is the 2Z and 1 plus 2Z. So only 2. So the order of this group is 2. Let's do something slightly harder. What's the order of Z mod 2Z cross Z mod 3Z? Alright, so here we have to actually work on this a little bit. Let's write down what elements this group actually consists of. So I'm just going to work it out here. So Z mod 2Z cross Z mod 3Z. What is in this group? First of all, there's the identity. 2Z, 3Z. And then I get all the possible combinations, right? So I can go 1 plus 2Z and 3Z. That's taking 1 plus 2Z on this coordinate and 0, so 3Z on the other one. So I exhausted all the possibilities where there is 0 on the second coordinate. So now I'm going to put 1 plus 3Z on the second coordinate. And so 2Z here. And then there's another option for having 1 plus 3Z on the second coordinate. That's 1 plus 2Z. 1 plus 3Z. Is there anything else? Is there any other option? Yeah, I mean, I had 3Z, 1 plus 3Z, so 2 plus 3Z. And then 2Z plus 1. Sorry, 1 plus 2Z. Two plus 3Z. Is that it? Well, so with 2Z I have 3Z, 1 plus 3Z, and 2 plus 3Z. And with 1 plus 2Z I have 3Z, 1 plus 3Z, and 2 plus 3Z. That exhausts all the possibilities. How many elements do I have? 6. So the order of this group is 6. What's the order of Z? Well, unsurprisingly, Z has infinitely many elements, so the order is infinite. What about something like Z cross Z mod 3Z? Well, look, even if I put just 3Z on the second coordinate, how many choices do I have for the first one? I can put any integer I want, comma 3Z, and that's already infinitely many elements. So this group is infinite. So that's a pretty simple notion, the order of a group. However, there is a more refined notion. Namely, I can look at elements in a group and ask about their orders. Now, we have to make a definition what that means, because of course it's not the same as just saying how many elements does one element have. All right? To make a definition, let me first introduce some notation. So let G be a group. With operation. Star. So I'm introducing the following. So let G be in G. And N be an integer. So I want to introduce what G to the N means. So when I write G to the N, I mean this. G star G star G. And that means there are n G's in this expression in total. N G's in total here. If n is positive. It's the identity if n is 0. And if n is negative, I just take G inverse instead of G and write a similar expression as the one in the top. So n G inverses in total if n is negative. Yeah, so for example, G cubed, that's just G star G star G. G cubed means I starred 3 of the G's together. G to the 7, that's G star G star G star G star G star G star G. How many G's? 1, 2, 3, 4, 5, 6, 7. G to the 0, by definition, that's E. What is G to minus 2? That's G inverse star G inverse. 2 inverses. G to the minus 5, that's G inverse star G inverse star G inverse star G inverse star G inverse. Okay, I mean, you can then prove some really easy formulas. So G to the N plus M, that's G to the N star G to the M. Note, I'm not putting any parentheses here because I know that the star operation is associative, so I don't need that. So that's one formula, G N minus M, that's G to the N star G inverse to the M. Or which is the same, right? That's G to the N star G to the minus M. And that's just clear directly from the definition. Okay, so if I have this notation, I can now define what the order of an element is. Definition. Let G be a group. Oh, sorry, capital G. Be a group. And let G be an element of the group. The smallest positive integer n such that G to the N is the identity. If it exists, if such n exists, is called the order of G. Denote it. Somewhat confusingly in the same way as the order of the group. if no such G exists, if no such N exists, we say that G is of infinite order. And write the order of G is equal to infinity. So let's do a few examples. One. Let's take the group G to be mu5. So I have 1, zeta 5 squared, zeta 5 cubed, and zeta 5 to the 4th, where zeta 5 is cosine 2 pi over 5. Plus I sine 2 pi over 5. Okay, so what are the orders of these elements? The order, let's just start with zeta 5. The operation is multiplication. So how many times do I need to multiply zeta 5 by itself to get to 1? So zeta 5 is not 1. Zeta 5 squared, so that's not 1. Zeta 5 cubed is also not 1. Zeta 5 to the 4th is also not 1. I mean, I kind of know where these things are, right? On the unit circle. This is zeta 5 squared, zeta 5 cubed, zeta 5 to the 4th. None of them is 1. But zeta 5 to the 5 is 1. So, the order of zeta 5 is 5. The smallest positive power that gave me 1 was 5. Let's try some other element. Zeta 5 squared, which isn't 1. Zeta 5 squared squared. That's zeta 5 to the 4th. That's also not 1. Zeta 5 squared cubed. That's zeta 5 to the 6th, which is zeta 5. That's also not 1. Zeta 5 squared to the 4th. That's zeta 5 to the 8th, which is zeta 5 cubed. That's also not 1. But zeta 5 squared to the 5. That's zeta 5 to the 10th, that's 1. So again, the order is 5. Similarly, I'm not going to do the calculation. Similarly, check that. The order of zeta 5 cubed is also 1. Sorry, 5. What haven't I checked? I haven't checked the identity. So I try. Identity to the power 1, that's already 1. Smallest positive power that gives me 1 is 1. So the order of identity is 1. So I have all the orders. Orders of all the elements are now known here. 5, 5, 5, and 1. In fact, the order of G is 1 if and only if G is the identity. You can think about it. This is just absolutely clear. Let's do another example. Alright, here operation is addition. So what are the elements? 4z, 1 plus 4z, 2 plus 4z, 3 plus 4z. What's the identity? 4z, so I know the order of this is 1. Now let's start with the other ones. Remember, the operation is addition, and I need to get back to the identity. The identity is 4z. So I start with 1 plus 4z. Well, that's to the power 1, so that is not equal to 1. That's not equal to 4z. So I do it twice now. That's also not the identity. 3 times. That is also not the identity. 4 times. That's 4 plus 4z. That is 4z. So this is this thing to the power 1, power 2, power 3, power 4. 4 was the smallest power that gave me the identity. So the order is 4. Now, one word about notation. The way I denoted things so far, I should have called this. You see, there's a reason why I wrote it out so laboriously. According to my notation, I should have written this. Alright? But that's awkward to write it like this, because that suggests I should cube it, use the multiplication in the ring z mod 4z. Why? That's not what I mean. I mean here to use the group operation. In this case, the group operation is addition. Okay? So, exception to notation, which I will sometimes use. If star is addition, we sometimes write ng instead of g to the n. Because that kind of makes more sense. It doesn't hurt the eyes so much if you do it this way. So normally we write g to the n, meaning you star the g itself with itself so that there are n g's. But when the operation is addition, I would rather not write that. I'm going to write 3, 1 plus 4z. And I'm going to write for this 2, 1 plus 4z. Okay, and this is 4, 1 plus 4z. Okay, let's continue. So this is one element in this group. What about other elements? 2 plus 4z. So 2 to the power 1, so 1 times that is back itself, that's not 1. I'm going to do 2 times that. So that's 2 plus 4z plus 2 plus 4z. This is 4 plus 4z, so 4z. Oh, so I did get the identity. And my power here in quotes is 2. So the order of 2 plus 4z is 2. Let's do 3 plus 4z. Well, 1 times that is 3 plus 4z, that's not 1. 2 times that. So if I add it to itself, I get 6 plus 4z. That is again not 4z. 3 times that. So that's 3 plus 3 plus 3, 9 plus 4z. That is 1 plus 4z. That is not 4z. But if I do it 4 times, I'm good. Because that's 12 plus 4z. And this is 4z. Okay, just to stress, right, where am I reading off the orders from? So the order here, right, so the order is 4. Just to be sure, right, where do I get this 4 from? That's this 4 here. The smallest positive integer, so that I add this element that many times, I get the identity. 4, the order of 1 plus 4z, I also had to do it 4 times, so that 4, is that 4? For this one, I got the order is 2, that 2 is that 2. And the order of this is 1. Okay, so I got 4 elements in the group. This is order 1. 1 plus 4z is order 4. 2 plus 4z is order 2. And 3 plus 4z is order 4. Example number 3, z, with addition. Well, I have infinitely many elements. I can't just list them, but let's think about that. First of all, what's the identity? It's 0. So 0 has order 1. Now let's take any positive integer. How many times do I have to add that integer to itself to get back to 0? That's not possible. If I take 7, add it to itself, you get 14, then 21, then 28, you never go back to 0. No positive integer will ever get you back to 0 when you add it to itself. So n is infinite. The order of n is infinite if n is a positive integer. What about if I start with a negative integer? Same thing, right? Negative 2 plus negative 2 is negative 4 plus negative 2 is negative 6. You never get back to 0. So positive or negative integer. So among the integers, everything has infinite order except for 0, which has order 1. Another example. 4. All right, okay. The operation here is multiplication, here it's addition. The identity is 1, 2z. Let's go through various elements here. So what does this group consist of? So it's 1, 2z, zeta 3, 2z. Well, this is cosine 2 pi over 3 plus I sine 2 pi over 3. Okay, and then 1 plus 2z. 2z. Zeta 3, 1 plus 2z, and zeta 3 squared, 1 plus 2z. All right, 6 elements in this group. So, if you want the order of the group, right, that's 6. But now the orders of elements. I'm not going to do all of them. I'm just going to do some to show you by example how this works. Let's try this one. To the power 1, that's the same element back, not the identity. Let's square this. How does this work? So I multiply the first coordinate by itself twice. The operation is multiplication, so it just gets squared. And this I'm adding to itself. But if I add 2z to itself, I get 2z again. Not the identity. Let's cube it. Oh, sorry. Cube it on the outside. So, this element with itself 3 times, right? Star. You do it coordinate-wise, so you get zeta 3 cubed. Because on the first coordinate you use multiplication, on the second coordinate you use addition, so you get 2z. But zeta 3 cubed is 1. So it does give you identity. So, the order of zeta 3 to z is 3. Because I needed to use power 3. Right? I needed to use power 3. Let's take some other element. So let's look at zeta 3 squared, 1 plus 2z. Okay, and that's, okay, so the first power I know it doesn't work, so let's do second power. So that means I'm squaring thing here, so I got this, and I'm adding this to itself. That's zeta 3 to z. Is that the identity? No. The identity is 1 to z. All right, let's do cube. So it's a square here. 1 plus 2z cubed. So I'm doing multiplying it by itself 3 times on the first coordinate. So I'm cubing it on the first coordinate. I get zeta 3 to the 6, comma, and I'm adding this to itself 3 times. So it's going to be 3 plus 2z. What is this? That's zeta 3 to the 6 is 1, and this is 1 plus 2z. It's again not the identity. Power 4. Okay, so that's this thing to the power 8, and here I'm adding it to itself 4 times, so it's this. Power 8, that gives me zeta 3 squared 2z. Not the identity. Wow, that one is really stubborn. Let's do the power 5. Zeta 3 squared 1 plus 2z to the power 5. So that's zeta 3 to the 10, 5 plus 2z. Which is zeta 3, power 10 is the same as power 1. That is still not the identity. Power 6. Oh, so that gives me zeta 3 to the 12, 6 plus 2z. That's the identity, because that is 1, and that is 2z. So the order is 6.